10-step design of a post-tensioned column-supported floor. The presentation objective. Today, practically all the column-supported post-tension floors are designed using specialty software. The objective of this presentation is to provide you with the engineering knowledge and depth of understanding of the floor design, knowledge and depth of the knowledge. The experience of this presentation helps you to enhance your evaluation of designs presented to you or you obtain using software, gives you in-depth understanding to evaluate designs presented to you by others. The presentation also provides you valuable background knowledge in modifying existing designs. That is very important if you have a design and you have to go through a change. This presentation gives you the background, in-depth knowledge which will enable you to do your job well. The information provided also empowers you to better evaluate a PT design and make engineering judgments. What are specific items that we will be focusing on? Learn the optimal sequence of design steps of post-tension floor systems. What I mean by that is there are different paths you can take to go through the design. The sequence that follows in this presentation shows you the optimal, the shortest path for the design. Become familiar with the application of ACI 318 and the 320 provisions for design of post-tensioned floors. Obtain hands-on experience on design of post-tension floors. Master the selection of amount and the layout of post-tensioned tendons. Master the treatment of tendons that are not continuous through the entire length of the member, discontinuous tendons. That is important. You rarely have a hand calculation in the literature that describes in detail how to handle discontinuous tendons. In this presentation, you get a detailed information on this topic. Become skilled in the determination of hyperstatic actions from members that are not prismatic. That is also important. The hyperstatic actions are integral in our design, the method used by most engineers, and this presentation goes through a detailed explanation. We follow 10 steps. Step number 1 is geometry and structural system definition. Then we define member properties. I am going through the optimal sequence of design. Then loads. Define design parameters. Then we calculate the actions, moments, and shears due to dead and live loads. We select post-tensioning. We check the design for serviceability compliance of the code. Then we code check for strength after serviceability. Then we check for transfer of pre-stressing, jacking at the time of jacking and applying the pre-stressing requirements will be explained. Then we go to detailing. Here I have a view of two post-tension flat slab construction. The one on the left uses a waffle slab construction. The one on the right uses bonded system. The one on the left is unbonded. The one on the right is bonded. Your step number one is selection of the structural system. And I have this diagram on the right which explains the options for selection of the system. The two-way system can be flat slab with drop, or slab with band. Here on the left, I show you the two-way system where the aspect ratio of the panel is such that you need in one direction additional strength because of its longer span. And it makes sense to make the slab slightly thicker rather than assuming a beam. And the beam will be used when the aspect ratio is beyond a value I have given here. So the options that you have are flat slab, that means uniform thickness throughout the way. You can have flat slab with drop cap or drop panel, and slab band. What I have shown here, this is the slab band. This is the two-way system shown on the top, which is subject matter of this presentation. Then the one-way system, ACI defines the slab to be one-way or two-way. That is the step number one, to make sure that you qualify for the two-way system requirements of the slab. In one-way system, you can have one-way slab spanning between the beams, this region here. This region of slab spanning between these beams or walls, that is regarded as a one-way system, designed in a different chapter of the code. Or you can have slab with interior beams. This here, this beam is a one-way system. The aspect ratio of a panel is the primary criterion regarding its structural system. In other words, this A over B determines whether you have to have this or a combination with the beam. We continue with geometry definition. Design the following residential column-supported post-tension floor system, which I have shown here. I have selected a floor here for design. The specifics of this is that the columns do not line up. I have purposely selected a system where the columns do not line up. Spans are of different length. It includes column drops for punching shear. Includes drop panels for moment and the shear transfer. It includes tendons that are likely to be discontinuous. In other words, it has the features that you encounter in common design, but it is not usually written in books because the examples in the books are often simple. Step number one, you subdivide the floor along the line of columns into design strips. These are the lines of columns, and we select support lines along the line of columns in two directions, and we associate slab tributary to each support line. It is important that every point of the slab to be covered by a design strip. These hatched areas become our design strips, and every portion of the slab should be covered by a given design strip. No portion of the slab should be left unassigned. We continue with the design by extracting and looking at the design strips one by one. In this case, I have selected one of the design strips. Select design strip and idealize it. Extract the design strip as I have shown here. Straighten the support lines. The support lines are like this, but we straighten the support lines. This presentation assumes that you're doing it yourself using first principles. You don't have a computer program, otherwise the computer program does that for you. So you extract the design strip, you straighten the support lines. These lines that are sloped are straightened here, and we end up with square boundaries. Next, we select the design strip which we had. We continue with the selection of the design strip. We model the slab frame with a row of supports above and below. We take a row of supports, columns in this case above, and columns below, one level above, one level below. The figure represents an upper level of multi-story concrete frame with supports above and below. We assume rotational fixity at the far end of the columns here. When we extract one floor, this is assumed fixed rotationally. We assume roller supports at the far ends of the columns. Here I have a roller support. Shows fixed but should be roller support so that the pre-compression would permit the shortening. So we have rotational fixity but roller support. Then coming to step number 2, material properties. I have assumed weight, concrete strength, modulus of elasticity, and long-term deflection creep coefficient of 2. Next, assume non-pre-stress reinforcement, 60 KSI, and the elastic modulus. For pre-stressing, the strand selected is ½ inch. Its diameter, it's 270 ksi. That is the strength of the common strand. And this effective strength, 175 ksi, we are not going to do a friction loss calculation because there will be at stressing some loss due to friction and the long-term effects. The effective residual stress is 175 ksi, and the modulus of elasticity, this is the number. Then next we go to live and dead load definition, dead and live definition. Self-weight is based on the member volume, superimposed 20 pound per square foot. That is what the ACI code requires. And the live load for residential, I have assumed 40 pound per square foot. Office is more, and then shopping mall more. These are the common values for a live load assumption. But for this assumption, for this example, I have taken 40 pounds per square foot. For lateral loads, wind and earthquake, the design is checked. We complete the design and detailing for gravity and check its adequacy for wind and earthquake where applicable. Then design codes. The applicable design codes are 318 and 320. 320 focuses on post-tensioning, and the 318 the other aspects of the design. There are other codes too, but the primary is 318 and 320. Next, we have to assume cover for reinforcement and post-tensioning. Assume that the slab is not exposed, so 3/4 of an inch cover is assumed in this example, where exposed cover has to be more. Cover to tendon is also 3/4 of an inch, will be more if it is exposed. In this example, I have taken 3/4 of an inch. Then when it comes to fire, the question arises whether the panel of each design strip is restrained or unrestrained. Restrained means it cannot easily expand when heated. Unrestrained means it can expand. For fire resistivity and its requirement, we look here and say this exterior panel, if not attached to a beam or wall, can expand out in case of fire, heat of fire. Therefore, this point is unrestrained. In the up-down direction, the argument is brought that this panel cannot easily expand up or down here as I have shown on a plan because of the constraint of the adjacent panel. Therefore, A will qualify as restrained, B qualify as unrestrained. And whether a slab is restrained or unrestrained, the cover for fire resistivity will be different. In this case, point A is considered restrained. Point A is considered restrained because of the adjacent connection. Point B is on an end span with no continuous support along the free edge and is viewed as unrestrained. And then we refer to a table which says if you want, for example, in this case, I have taken 2-hour fire rating. If it is unrestrained, this is the cover. If it is restrained, this will be the cover. I have taken 3/4 of an inch cover. Listed down here, restrained 3/4 of an inch. We select the post-tensioning system. I have selected unbonded. It can be unbonded or bonded. And here is an example of the anchorage or stressing end of an unbonded system. Example of anchorage and or stressing end, in this case a stressing end of a bonded system, is shown here on the right, where you will use the tube to inject grout in the void of this duct after the strands are stressed. Next, we select design parameters. ACI focuses allowable stress as focuses on limitation of stresses to an allowable value. And I have listed here the allowable values for slabs. Tension shall not exceed this amount, and compression this amount. For frequent or sustained load, total load combinations, sustained load combinations are a little bit different. The difference between the total and sustained is total is the load given in the code for which the slab has to be designed. Sustained is in ACI left to the judgment of the design engineer that during its lifespan the slab is not going to be loaded to the maximum allowable value. Live load specifically here will be on, off, or often at the less magnitude than the maximum. So there can be larger allowable values. If we have sustained free in service condition, and this is the for design value. The fraction of the sustained is not given in the code. The allowable value is given, but it is left to the judgment of the design engineer to select what fraction of live load is likely to be on the slab over its average over its lifespan. Now, allowable deflections. Allowable deflections for dead and live is given span over 240. This can be corrected by camber or topping. Then there's live load deflection span over 360. That is difficult to correct if it exceeds. Deflection subsequent to installation of elements that are likely to be damaged. Brittle members subsequent to installation of them, it is a span over 400. The most critical one to consider in design is live load deflection. Others are amenable to control. Long-term deflection is used by assuming a magnification factor 2 due to creep on the immediate deflection. Next, we calculate the actions, moments and shears due to dead and live load. Analyze the design strip as a single level frame with one row of supports above and below. The dead load moment is calculated as I show here, and you write down the left of the support, right of the support, and mid-span. For hand calculation, we limit ourselves to 3 points: left, right, center. If there's a computer program that you use, it will check it at more points along the span. This is live load deflection, left, right, and center. The values are at the face of support and mid-span. Next, item 6, we move to post-tensioning. We have to select our design parameters. We select the force of post-tensioning and its profile, and we assume an effective long-term force that each strand will provide. There are other options where you can design the member recognizing the change in force along the tendon length. But for hand calculation, we will not do so. We assume a force uniform along the member. When it comes to method of design, there are 3 methods for design explained in another presentation of this series. But the common practice, almost universal practice, is to use load balancing method. In load balancing method, you select the post-tensioning to provide uplift for a percentage of the other loads and go through the steps as I will describe in the following pages. Then we calculate the actions from post-tensioning due to balanced loads. Before going to selection of post-tensioning, I want to draw your attention to something specific to post-tensioning. The figure on the top right shows conventionally reinforced concrete. The one on the bottom shows post-tensioned. The one on the right for the calculation of rebar, you calculate the moment wherever you have a bending moment, you can calculate an associated rebar. But the one on the top, which is post-tensioned, in addition to the definition of geometry of the member, its material properties, and loads, the post-tensioning requires two additional input to complete the design. One of them is the pre-compression, how much force you want to put. What I mean is after you know the geometry, after you know the load, after you know the concrete properties, if you're dealing with conventionally reinforced member, you're done. There will be a bending moment and there will be an associated required rebar. But when you come to post-tensioning, in addition to what I just mentioned, that means the geometry, the load, you need two more things. How much pre-compression? In other words, the pre-compression is not determined by calculation. The way we do in the load balancing, it is an input rather than calculated value. So you need to know how much pre-compression as an assumption. Also, what percentage of dead load you balance. What I really mean, the profile. The profile determines how much uplift you will have. This is assumption. So you need to make two assumptions which are not coming out of calculation but are based on your experience and judgment. So we assume 150 psi, that is one assumption, as input. Can be 200. Code says 125, and then the code has a minimum value, but I have assumed here 150 psi. 125 is the minimum code requirement. Now, what percentage of dead load we balance? This is our assumption. I have assumed 60%. It's not often economical to balance more. So these are the two assumptions which are not arrived at from the design, but are input by you as an engineer. With these two assumptions, we select a tendon shape, a tendon profile. I have given here the shape of a parabola, non-symmetrical parabola, and loaded, pulled. It's a tendon pulled with force P. There will be forces acting up. In design, because typically the length is much more than the drop, it is assumed that the force is applied upward and it is uniform in magnitude. It's a close assumption and it's universally used. So there will be an uplift assumed uniform and its magnitude is given here. The magnitude depends on the geometry and the force. At construction time, tendons will be laid out somewhat differently, not exactly like I have. Maybe in the next slide we will see it. I assume an effective force for tendon, which is 226.77 kips per tendon based on 175 KSI, and this is the strand area times its effective stress for unbonded tendons. So the force per tendon 450 psi. So the force that each tendon with 150, or let me put it this way, knowing the force per tendon and 150 psi, I can work out how many tendons I need looking at the cross section of the slab. I look at span number 1, the force needed at span number 1. I take the cross section of the span. This is the width of the span. This is the thickness of the span. The width of the span, 12 inches, and 150 psi is what I assumed. I need so much force for span number 1. And each tendon gives me 26.77, so I need 16.77 strand for span number 1. I assume 17 strands for span number 1. I follow the same scheme. Take span number 2, calculate its area, multiply by 150 and divided by the force that each strand provides, and I end up the number of strands that each will be requiring. I show the number of strands. In here, I assume 20 strands for the first 2 spans, 23 strands for the third and fourth span. So there will be 3 strands which from span 3 extend over the support to span number 2. And I have assumed here a column drop, and a drop panel. Drop panel is larger than the column drop. It provides resistance for bending moment, which extends farther away from the face of the column, and this is for punching shear. So I have a column drop, and I have a drop panel. In hand calculation, I assume simple parabola. In real structure, these will be smooth, reversed parabola over the section. We have to account for the terminated tendons and changes in geometry of the concrete member. I want to draw the attention to that we have a change in geometry which impacts our design, and we have a discontinuous tendon which also impacts our design. The number of strands are shown here at the bottom right. I have to calculate the force that the post-tensioning applies to the design strip. That is, so to say, the balanced load. We calculate the post-tensioning balanced load. I have started with span number 1. In span number 1, the tendon will be anchored at the centroid here. It will be high point over the, so to say, support. The geometry of the tendon is as shown here. The formula that governs this geometry is there. So knowing that this is at the mid depth and knowing that this is at the top and knowing the span, I can find the location of the low point, and knowing the number of strands, I can calculate the upward force. So I have A, here is A, I have B, I know this, I know the length, so I can calculate using this formula the distance to the low point. I have the force P because I know how many strands I have. So the formula that gives me the uplift is this. This is the uniform upward force 0.106 kips per linear foot. The total uplift for the 20 strands will be this. The percentage of uplift I have obtained is 56%, less than 60% that I wanted, but I have considered it acceptable. Then I go to span number 2. In span number 2, there are 20 continuous tendons and 3 tendons which come from span 3 and extend to span number 2. So first, balance loads of span number 2, which consists of lateral force from continuous tendons, lateral force from terminated tendons, and moments from change in centroidal axis, because I think we have a drop panel or column drop. We will look at it shortly. For the continuous strands, this is the formula. The uplift is this. The percentage of uplift is 56%, assumed acceptable. For the continuous tendons, we have reactions because of the tendon at left and right. Now we go to balanced load of terminated tendons. In span number 2, we have 3 tendons coming from span number 3. 3 tendons coming from span number 3, terminating in span number 2. The extended tendons will create also forces, downward force here, and at the end uplift. The relationship for the uplift and downward force is given here. This is the distance. I have taken it as 1/5 of the span. Typically, you extend the tendon about 1/5 of the span. So I calculate this downward and upward force. The length of the span is total 32.75 feet. The extension here is this much. Tendon force is this much each. I have 3 of them. So for uniform force WB, this will be so much. The concentrated force is given by this value. That is the concentrated force. So I have the force from extended tendon. Next, we come to the consideration of the thickening of span number 2. We have to calculate the balance loads from shift in member centroid at column drop. There is the centroid of the member in the slab is here. In the column drop, the centroid is here. So there will be a shift. There will be a bending moment because of the shift in the centroidal axis. The moment is equal to the force times the shift in centroid. Here is given. I have the force and I have the distances to the centroids. I have the distances here and here, so I can calculate the shift E, and the moment is so much. This moment will be exerted at this location. Next, I set up the balanced load. The balanced load is the load that the post-tensioning applies to the member. It consists of up and down forces, up and down forces, down force at the tendon ends, upward force over the continuation of tendon, and also it has bending moments. Wherever there is a change in centroidal axis, there will be bending moment. So here I have shown the entire balance load, the entire forces that the tendon applies to the member, consisting of up and down and moments. We have to check the validity of the balance loads to make sure that we haven't made a mistake. The check will be by static equilibrium. The post-tensioning forces, or the forces that post-tensioning applies to a member, is always in equilibrium. Always in equilibrium. So for this to be correct, it should be in equilibrium. Sum of forces must add up to 0. In other words, if in the upper diagram I add up the forces up and down, they must add up to 0. Sum of moments must add up to 0. If I take moments anywhere of this on the top and this on the bottom added together, the moment when you take moments, you have to consider both of them. The sum of moments must be 0. If this is not satisfied, it means we've made a mistake or we've disregarded something in creation of balanced loads. We have to go back and make correction. Why do we have to go back and make correction? Because the consequence of an error here could be on the safe side or on the unsafe side. And unless you know whether your assumption leads to a safe solution, you have to go and correct it. And in this case, we just add up the numbers together to see what it comes out correct errors if equilibrium is not satisfied. In the figure shown, the sum of up and down forces must add up to zero. Moment of forces in A and actions in B. And this adds up to zero. I have done the check. After we verify the correctness of the balance load, we apply the balance load to the frame program in the way that we applied the dead load and the live load. Now we apply the balance load to our frame program. Application of balance load to the frame program gives us the bending moment diagram on the top due to post-tensioning, and the reactions. I have written the reactions of connection of the supports to the member. At the bottom is the reactions, axial plus moments at the top and bottom. The top are moments from post-tensioning, bottom are reactions from post-tensioning. Why do I show the reactions from post-tensioning? Because the secondary hyperstatic actions in post-tensioning are created by the reactions. I use the moments at the top to do stress check, to do deflection check, but I use the bending moments at the bottom for safety check. The one at the top for service condition, the one at the bottom is for safety condition. So we calculate the actions from balance load, and these are the actions. The calculation is the result of us applying the balance loads of the previous screen to the frame of the structure. We obtain actions at the face of supports and at midspans for hand calculation. Face of support and midspan. If you have a computer program, it does it most probably at other points also. Note the reactions. The reactions are hyperstatic forces. This is the definition of hyperstatic forces. Moments will be used for service check here. Reactions will be used for strength check. The reactions from post-tensioning must always add up to zero. These must always be zero because the post-tensioning itself, the balance loads which we applied to the frame were in equilibrium, therefore these must add up to zero also. Next, I'm going to do service check. I calculated the actions from post-tensioning. I have calculated the actions for dead and live. Now I do service check. That is step number 7. For service check, we have to do stress check. We start with stress check. This is a must. ACI does not provide a remedy if your stress check fails. The European code EC2 has a way you can bypass it, but for ACI you must satisfy it. Then we do deflection check, and that is a live load deflection check. Again, ACI has no remedy for live load deflection check not satisfying. These are the 2 checks that must pass, otherwise you abandon your design and redo it with new parameters. Minimum reinforcement must be provided also, but that is simple. You can always provide minimum rebar that is given in the code. There is no issue there. First, what load combinations do we use? The common practice is to use this load combination: one dead, one live, one PT. Total load combination. For long-term deflection, we use this load combination, which has a lower value of live load. That 0.3, which is for frequent, is not given in ACI. It is left to the judgment of engineer. I have taken the coefficient given in the European code. This is for long-term deflection. This is for immediate deflection. Now, using engineering judgment, we select the location where stress check should be carried out. In hand calculation, typically face of support and midspan is used. And at each selected location, we use the design actions applicable to the entire design section. That means the entire cross-sectional, and apply them to the entire cross-section of the design strip to arrive at code intended hypothetical stress for code compliance. For code compliance, we take the entire action calculated and we apply it to the entire cross-sectional area of the design strip, and we obtain one value, one stress, one precompression, and then we compare that one value with the permissible value of the code. In other words, use the integral of the action on the design section, apply the value to the entire cross-section of the design section, and arrive at one single value for code check. And this is the formula we use. Dead load, live load, post-tensioning moment, all added together, divided by section modulus, and we add to it pre-compression, obtain a single extreme fiber stress. This is section modulus. We do deflection check next. We read the deflection due to dead load, live load, and post-tensioning from our frame program. We check the live load deflection. Live load deflection should be less than span divided by 360. Live load deflection must be satisfied. If not satisfied, you redesign. Live load deflection has nothing to do with the amount of post-tensioning. Live load deflection depends only on the geometry of the concrete structure and its material property. Material property, concrete structure. If live load deflection is not satisfied, you stop and do redesign. You have to change either concrete strength or slab thickness. No other remedy. And then we check long-term deflections. For long-term deflection, we assume 30% of the live load to be sustained, to be on the member at all time. And we assume a creep coefficient of 2. And this is the formula I use. 1 is immediate, 2 times creep of dead load and post-tensioning, but a fraction of live load. This is the immediate action due to live load added to the long term. And this has to be less than 200, span over 240 for visual sense of comfort and malfunction of the installations on the slab that are sensitive to deformation. If not satisfied, use camber cover to the slab. I'm talking about this 240, not the live load. That live load you have to redesign, but for this other requirements, there might be remedy. The long-term deflection can be exceeded if larger values are acceptable for the specific application. Then we go to, once we are done with the deflection check, we go to minimum rebar. ACI requires that you put a minimum amount of bonded reinforcement over the support and possibly in the span. So we check over the support and its requirement in the span. This is the flow chart that you start from here. If you are unbonded, you go here. If you use bonded, you go here. And each of these circles refer to the detailed description, which is in the book at the end of this presentation. The flowchart gives the conditions of and the amount of the minimum bonded reinforcement. The encircled numbers, here encircled numbers, refer to the description of each of these requirements. First, on the top of the support, you have to have minimum bonded. Bonded reinforcement is required over the support and possibly in span. Over the support, bonded is required irrespective of whether you use unbonded or bonded tendons. The rebar over the support is function of geometry of the design strip and the design strip in the orthogonal direction. It is the function of this design strip and the design strip normal to it. And it depends on the cross-sectional here and here. Using this formula, the reinforcement required is this fraction times the area, cross-sectional area of the design section. You select the larger cross-sectional area of the two sides, and you provide the bonded reinforcement irrespective of whether you use unbonded or bonded tendons. ACI does not recognize the bond of the grouted tendons, bonded tendons, to provide the required bond for ductility. Rebar over the support is function of the geometry that I explained before. In the span, it is function of the hypothetical tensile stress. You calculate the tensile stress at the bottom of the span at mid depth, at extreme fiber at midspan, and depending on the size magnitude of the tension stress, you may or you may not need bonded reinforcement. What I have shown here is the section at mid depth. This is the top through the depth of the slab. Top of the slab, bottom of the slab, tension at the bottom of the slab. If this tension at the bottom of the slab exceeds this value, then you have to calculate the force that the tensile region of the slab provides, this force, and provide rebar. The amount of rebar depends on the force resisted by rebar using half its yield stress. After having gone through the minimum rebar, then we go into strength check. For a strength check, we need to know what is the demand moment, demand shear, and then we check the section to be adequate to resist it. If balance loading is used, which most engineers use balance loading, that is the common practice in the US, we have to calculate the hyperstatic actions from post-tensioning and include them in our load combination. This is required if we use balanced load method of design. The load combination for service is this: dead load, live load, and post-tensioning. But for safety, the dead load and live load moments are the same. The coefficients change. Here's 1, here's 1.2. But for post-tensioning, the magnitude changes and the coefficient changes. So the objective of repeating the load combination is to emphasize that the magnitude of the quantity changes in the two, and obviously the coefficient. So we have to calculate the hyperstatic actions from post-tensioning. Calculation of hyperstatic actions for formation of design moment. We calculate moment capacity of section based on its post-tensioning and rebar from previous sections. I want to repeat this. After we calculate the design moment, rather than design the section to resist the demand, we look at the section and we observe that it has post-tensioning tendon in it. It has minimum rebar in it from serviceability. So post-tensioning and minimum rebar provide some capacity, and design based on ACI are such that in many cases, I would say in most cases, the capacity is more than demand. So we let it be. In other words, rather than doing design, by that I mean calculating how much rebar you need, you go and calculate how much capacity you have and compare it with demand. After that, we do a punching shear check, which is required. After punching shear, we do some detailing. One of the detailing instances is to take care of the unbalanced column moment at the support. I will describe that in greater detail in the following slides. Load combination using balance method of design is this: 1.2 dead, 1.65, and 1 hyperstatic. The second load combination is required to be checked but rarely governs. HYP is the hyperstatic action. So we have to calculate the hyperstatic actions. We use the direct method based on reactions. There are different ways to calculate hyperstatic actions. I have used the direct method. This direct method applies to all conditions. In the direct method, you calculate the moments, hyperstatic moments shown at the bottom here, directly from reactions of the post-tensioning. Diagram on the right shows the column reactions and column moments. We look at the column moments and column reactions and build from this information the moment diagram associated with it. We say here I have 62 and I have 62, 62 and 62 add up together to 124. So I have 124. But then there's a reaction here as you move to the right. This 124 drops because of this reaction. And then I take moments here and I have this value. This is very simple calculation. You just take a section and take moments of whatever forces you have and you build this. The diagram at the bottom is the distribution of moment which I will have to include in the load combination. The reactions from post-tensioning are applied to get the hyperstatic value. The reactions shown in A are in equilibrium. This is what we had before. B shows the moments that are derived from the reactions here. These moments are derived from up there. B is the hyperstatic moments. Yes, we had this. Then, rather than design, I calculate the capacity. I have shown a section here. There is post-tensioning. There is rebar. So the forces on the section are likely to be combinations of concrete compression, tension from post-tensioning, and rebar. In the following conditions, if the following conditions are met, the reactions moment are met, the reactions moment capacity can be approximated based on the following. What I mean is if the following is met, the capacity can be estimated. You can use the ACI code formula, which is fine. But if you want a simpler but conservative way, the following would work. If the concrete is more than 4,000 psi, and if the depth of the compression zone is less than this ratio, depth of compression zone divided by the distance to the farthest rebar. C is the depth of compression zone. and tendon length less than 125 feet. Each stressing length. If more, it is stressed at two ends. It is 250 feet, the limit for two-end stressing. Then you can conservatively assume 215 KSI for spans which are less than 35 feet and 195 KSI for spans that are more than 35 feet. Now, this is a conservative suggestion bypassing the more complex code formula to be on the safe side. Or if you want to be even more conservative, you assume each tendon, you substitute each tendon by 3 times its area and assume that it is rebar. You estimate the capacity assuming that the tendon is rebar, but its area is 3 times rebar area. Why this works? This works for ACI, but not for European code, because in ACI we have strict requirements to satisfy serviceability. And by the time you're done with serviceability, most probably you have more post-tensioning and rebar that is needed for safety. This is the strain diagram. This is the stress diagram. Depth of compression zone. For ductility, the depth of the compression zone, C, should be less than a fraction of the distance to the farthest rebar. This provision guarantees that under bending, steel yields before concrete crushes. You yield here before crushing of concrete, so there will be warning to others of pending failure. To reduce the depth of compression zone for ductility requirements, you can add compression rebar. Adding compression rebar will reduce C as a remedy. We move into detailing. One requirement of detailing is a transfer of unbalanced column moment. Unbalanced column moment is defined as the difference between design of moments on the opposite sides of slab at column connections. This is the moment that is resisted by the slab. If at a point you have column connection to the slab and the connection is such that moment is transferred between the slab and column, the amount of moment that is transferred is defined as unbalanced moment. And that unbalanced moment I have tried to show here. This is the column, moment in the slab on one side, moment in the slab on the other side. The difference between the moment in the slab at the face of column is the unbalanced moment. The reinforcement that is associated with this has to be placed within a narrow band. That reinforcement is available because we have, in each case, we design the slab for the entire moment that is present. It, the reinforcement in the slab associated with the transfer on unbalanced moment must be placed over a narrow band at the slab. In most cases, the provision leads to detailing requirements as opposed to added rebar, since the determination of reinforcement in the slab included the contribution of column connection. When we designed the slab, we designed it for this and we designed it for this. So we have the reinforcement. It's placement. Reinforcement required to resist column moment must be placed within the effective width of the support, and the effective width of the support over the column is defined to be this length, 1.5 times slab thickness on each side. Then we come to punching shear. For punching shear, ACI assumes that the transfer takes place according to a diagram like this. You will have an assumed perimeter and surface, and you consider the moment about the column in each direction. Separately, you apply it to the surface and you apply the axial. You have axial and you have moment, you have stresses, and you calculate the stresses to be the sum of the two. That stress has to be less than the permissible value, otherwise you put reinforcement, punching shear reinforcement, provided that the stress is within allowable. Next, transfer of pre-stressing. At the time we apply the jacking force, tendon has its maximum force. Concrete is the weakest in strength. It is young. Live load is not there to counteract the uplift of the tendons. So the likelihood of concrete spalling exists if the location is overstressed. You add rebar where the representative tension stresses exceed the allowable threshold. You calculate, like dead load and live load, a representative extreme fiber tension stress for the design strip, very much like the dead and live load calculation. If it exceeds the allowable tension, you add rebar or you wait until the concrete strength is adequate. You do not exceed representative compression stresses. If compressive stresses exceed, you wait until concrete gains adequate strength for the representative stress. Otherwise, there can be failure at stressing. The load combination for the check of tension and compression is this. Not given in ACI, but it is used by engineers in common practice. It is self-weight plus a larger fraction of PT assumed in long term because losses have not taken place. The allowable stresses for tension and compression are these. If tension exceeds, you put rebar in this amount. N is the tensile force. If compression exceeds, you wait. Then last step is detailing. Detailing consists of top bar and bottom bar, position of the bars, and the length of the bars. Position of the bars are shown here with their length given down here. Top bar extends clear span over 6 from the face of the column. Bottom bars are 1/3 of the clear span, centered. Top bars and bottom bars. So in summary, I defined the geometry, that was step number 1, defined material properties, defined loads, defined design parameters, then calculated the moments due to dead and live loads. We selected post-tensioning using two assumptions, pre-compression and uplift, to enable us to come up with the initial post-tensioning. We calculated the values from post-tensioning and did serviceability check. We moved to strength check and did also check for transfer of pre-stressing at time of stressing and did detailing. That brings me to the conclusion of this presentation. Thank you for listening. The information was from a chapter of this book.